So, we have seen various symmetry operations in various symmetry groups. Now, what we want to do is to work our way towards writing what is called the character table of a group. Okay. So, the character table of a group is how groups are typically represented, and the character table gives you all the information you need to know about the group. Okay. So, we will try to work our way towards that. One important concept in order to understand the character table is what is called as representations of groups. Okay. So, representations of groups is one important idea, and to illustrate this, I am going to go back to something that you have already seen before, which is the matrix of transformation of the group. Okay. And this is something that you have seen before. Suppose I have an arbitrary point, okay, and I operate it. This is an operation in the group. Okay. So, suppose I perform an operation on an arbitrary point, then I get some resulting point x prime, y prime and z prime. Okay. So, any operation in a group can be thought of as something that transforms one point to another point. Okay. And the most general object, okay, one very general object that transforms a vector into another vector or a point in Cartesian coordinates to another point is what is called a matrix. Okay. So, you can imagine that if I multiply this by a matrix, then I will get this new point. Okay. And in fact, these are the kinds of operations that we will be considering. Okay. These are linear operations, and so these are the operations that turn out to be related to the various symmetries of the various symmetry elements. Okay. So, for example, suppose operator is the identity operation. So, identity operation okay. So, the identity operation you can immediately see then x prime, y prime, z prime is equal to x, y, z. Okay. So, this implies x prime equal to x, y prime equal to y, z prime equal to z. So, this is very clear, and what you can say is that you have x, y, z, and the matrix that accomplishes this transformation x, y, z. Okay. So, if you want to multiply a matrix to x, y, z to get x, y, z, that matrix has to be the identity matrix. Okay. So, this is your identity matrix. Okay. So, then you say that identity is represented as 1 1 1 0 0 0. Okay. In other words, this matrix is a representation of the identity operation. Okay. So, this matrix is a representation of this identity operation. Okay. Now, suppose the group has other operations. So, let us take another example. Suppose O is equal to C n. Okay. So, a rotation 2 pi by n. Okay. So, then you can show that when you rotate, so this is rotation by 2 pi by n, okay, by this angle. Now, when you rotate by this angle, you can clearly see what will happen. Suppose I take a point x, y, z and I rotate by 2 pi by n. Okay. I rotate by 2 pi by n, and let us say assume C n axis is z axis. Okay. So, assume that the C n axis is a z axis. So, you are rotating about the z axis by 2 pi by n, and when you do that, then you know that your x prime is equal to x cos theta plus y sin theta, y prime is equal to minus x sin theta plus y cos theta, and z prime equal to z. Okay. So, immediately this implies your O operation is represented by cos theta, sin theta, 0, minus sin theta, cos theta 0, 1. So, this is a representation of C n, or where you should mention. So, theta equal to 2 pi by n. Okay. So, this with theta equal to 2 pi by n is a representation of the C n operation. So, the C n symmetry operation is represented by this matrix, the identity is represented by this matrix. Similarly, we can represent other operations also by this matrix, but I won't go into the details. You can take a group and you can represent every operation in a group in this matrix form. So, every symmetry operation in the group can be represented as a 3 by 3 matrix. Okay. So, every symmetry or each and every symmetry operation can be represented as a 3 by 3 matrix. Now, there is one more thing about this representation, and that has to do with the products. So, products of symmetry operations Okay. So, product symmetry operations means you operate by one symmetry operation and then by the other. Okay. So, that corresponds to first operating by one matrix and then by another matrix. So, you operate by one matrix to get this, then you operate on this matrix to get on this vector to get the final vector. Okay. And this can be represented as products of matrices. So, that means the representation of a product of operations is nothing but the product of the representations, and you can see this very easily. Suppose I take C n, multiply it by C n. Okay, and let us say for convenience we will take n equal to 3. Okay, if n equal to 3, then C n times C n. Okay, so, this is C of 2 pi by 3, this is rotation by this is equal to C 3 square. Okay. Now, C 3 square corresponds to rotation by minus 120 degrees. Okay. So, C n is rotation by 120 degrees, or C 3 is rotation by 120 degrees, C 3 square is rotation by minus 120 degrees, and C 3 square can be calculated in this way. Okay. So, you start with C 3 is nothing but cos 120 sin 120 0 minus sin 120 cos 120 0 0 0 1. Okay, now, cos 120 is minus half, sin 120 is root 3 by 2 0 minus root 3 by 2 minus half 0 0 0 1. Okay. So, C 3 is represented by this matrix. So, C 3 is represented by this matrix. Okay. Now, So, the next question is what about C3 square? So, C3 square will just be this matrix multiplied by itself. So, you can evaluate. So, C3 square is equal to minus half root 3 by 2 0 root 3 by 2 or minus root 3 by 2 minus half 0 0 0 1. Okay. And if you do this, so this multiplied by itself and if you take this product you can see what you get. So, the first term will be plus 1 by 4 minus 3 by 4. Okay. So, plus 1 by 4 minus 3 by 4, that is minus half. Okay. So, you can easily see plus 1 by 4 minus 3 by 4, that is minus half. The second the second term will be minus root 3 by 4 minus root 3 by 4. So, that is minus root 3 by 2, and the third term you can see it is just 0. Okay. Similarly, what you can show is that this term is plus root 3 by 4 plus root 3 by 4, that is root 3 by 2. Okay. This is again minus half 0 0 0 1. Okay. Now, you can immediately look at this and you can say that you can see that this is cos of minus 120. So, cos minus 120. So, this is, or you can say cos 240 sin 240 0 minus sin 240 cos 240 0 0 0 1. Okay. So, what it means is that this is nothing but the matrix representation of C3 square, and so this matrix product is a valid way of doing the matrix representation. Okay. So, you verified. So, this verifies that this is nothing but a representation of C3 square. So, C3 square is represented by this matrix. Okay. So, what we notice is that this matrix representation preserves the products. Okay. So, this is a valid representation. Okay. Now, the other property of this representation has to do with the nature of these matrices. Okay. So, the other property has to do with the nature of these matrices, and what we notice is that if I take, so you notice that C3 square okay, has to be equal to C3 inverse. Okay. And what you notice is the following, this is nothing. So, you look at C3 inverse. So, C3 inverse is this, okay, C3 square is C3 inverse, and you notice C3 inverse and C3. Okay. So, you notice that C3 inverse looks exactly like C3, only these two elements are shift switched, and in fact, you can see that since the other off diagonal elements are the same. So, you see that C3 inverse is equal to C3 transpose. Okay. So, C3 inverse. So, the inverse of C3, which is C3 square, is C3 transpose. Okay. This implies C3 is an orthogonal matrix. Okay. And you recall when you were doing the matrix of rotations that orthogonal matrices, they preserve the dot product, they preserve the length of a vector. Okay. So, transformation by an orthogonal matrix preserves the length of a vector, and it is very important that all the symmetry operations should preserve the length of this vector x y z. Okay. So, all symmetry operations are represented by orthogonal matrices. In order to preserve lengths. Okay, so this is a feature of all the matrix representations of symmetry operations. So, all symmetry operations are represented by orthogonal matrices in order to preserve lengths. The other feature that we see in this representation is that these are square matrices, square or 3 by 3 matrices, square 3 by 3 matrices. Okay. Now, for square matrices, a property of a matrix that is fairly useful is called the trace. Trace is equal to sum of diagonal elements. So, you define, so this is the definition of the trace, and what you notice is that trace of C 3 is equal to trace of C 3 square. Okay. So, trace of C 3 in this representation, trace of C 3 is trace of C 3 square, okay. And there is a deeper meaning to this. Okay. So, in general, trace of A B is equal to trace of B A, okay. And trace of A B C is equal to trace of C B A of B C A, okay. This should be B C A. So, you can do a cyclic permutation. So, you can get C A B is equal to trace of B C A. Okay. So, the trace has this cyclic property. Okay. Now, this tells you something very useful. See, suppose I take, so therefore, trace of x inverse A x. Okay. So, trace of x inverse A x is nothing but trace of x inverse A is equal to trace of A. X inverse is just identity. So, trace of identity times A is just A. So, trace of x inverse A x is just trace of A. So, this implies that conjugate or similar matrices have same trace. Okay. So, the trace of two matrices which are related through this similarity transformation are identical. Okay. And what we already saw is that what we have already seen is that elements belonging to a class, so various elements belonging to a class are related to each other through this similarity transformation. Okay. So, if A and B are in same class, same conjugacy class, okay, then there exists x belonging to group G such that B is equal to x inverse A x. Okay. So, we immediately see that therefore, if A and B are in the same class, so this implies trace of A is equal to trace of B, okay, where A is the matrix representation of A, the matrix representation of B. So, the matrix representations of A and B have identical traces. matrix representations of operations that are in the same class have identical traces. Okay. I want to emphasize right now that this 3 by 3 matrix that we have been talking about is just an example of a representation. Okay. We will also see other representations that are possible, but the 3 by 3 matrix, since you have seen this before, I want to use this example to motivate the representations. Okay. So, now now trace is also called character. Okay, character of symmetry operation in the particular in the 3 by 3 representation. Okay. So, this so when you represent the symmetry operation as a 3 by 3 matrix, then the trace is said to be the character of that symmetry operations. So, what we notice is that all elements belonging to a class have same character, and I will mention this. This is we will say they have the same character in any representation, any representation. And here I have generalized from the 3 by 3 matrix to a more general representation. Okay. So, now we are all set to actually go towards character tables. Okay. So, what we want to lead towards is something called character tables, which are like the group multiplication tables, but they are represented in terms of conjugacy classes and representations. Okay. So, now let us go to a more general definition of representation. Of a group. Okay. So, we have looked at this example and we have seen how to use the 3 by 3 matrix. So, the definition of representation of a group, the general definition is that this is a set of square matrices corresponding to various operations. Okay. So, that means each operation has a square matrix associated with it, such that products of matrices represent products of operations. Okay. So, if I have two symmetry operations A and B, okay, then suppose I have A and I have M A is the representation of A. This is representation. So, this is a matrix that represents A. Okay. So, if I had A is an operation and M A is its representation. Okay. Similarly, if I had B which had a representation M B. Okay. So, A is represented by a matrix M A, B is represented by a matrix M B, then the product A B should be represented by first operate by B. So, it is this way M B M A, okay, M A M B. Okay. So, A B is represented by M A M B, and if this is true for all elements of the group, then this is a valid representation. Okay. So, you have to have this satisfied for all the elements, all the symmetrical operations of the group, and then it becomes a valid representation. Okay. So, now once we have the representation, it is very obvious to say what is the character of a representation, and a character is nothing but the trace of character of A. So, if you say trace of M A, this is the character of A in given representation. Okay. So, if you have a representation in which A is represented by a matrix, then the trace of M A is called the character of A in that representation. Similarly, for trace of B and trace of M A M B. Okay. Now, suppose I take the identity, suppose I take identity. Okay. So, suppose I take identity and this is represented by a matrix M E. Okay. Then clearly, if M E okay, so the trace of this matrix is just going to be the number of rows. Okay. So, is just equal to the number of rows or columns in M E. Okay. So, the trace of identity is just the size of the matrix. So, if it is a 3 by 3 matrix, the trace of the identity will just be 3, because you can see that identity corresponds to 1 along the diagonals and 0 everywhere else. So, the trace is just number of rows. Okay. So, and this will be true in any representation. If you have a 2 by 2 representation, the trace of identity will be 2. If you have a just a one dimensional representation, then the trace of identity will just be 1. Okay. And this is also called dimensionality of representation. Okay. So, the number of rows or columns of M E is called the dimensionality of that representation. So, if you have a 3 dimensional representation, so our 3 by 3 matrix was an example of a 3 dimensional representation, where the trace of identity was 3. Okay. So, it will turn out that the character or the trace of various symmetry operations, okay, is what will enter the character table, and you can immediately see that since all elements of the same class have the same characters. Okay. So, we like to group the operations based on classes, and then we will write the trace of those, we will write the character of each of those classes. Okay. So, let us take a very simple example. Okay. So, we will just take a simple example. Let us take C2V. Okay. C2V consists of 4 operations. It consists of E, C2, sigma V and sigma V prime. Okay. So, and similarly, so then we can do the group multiplication table. So, the group multiplication table will be E times sigma V times, this should be identity. Okay, sigma V, this will be C2, C2 times C2 is identity, C2 times sigma V is sigma V prime, sigma V prime, sigma V. So, this is the multiplication table of this C2V group, and what we can immediately see is that now we want a representation that maintains all these products. Okay. So, let us look at various representations. First, let us look at a very trivial representation. So, E is equal to 1. So, 1 is basically a 1 by 1 matrix. Okay. E is 1, C2 is 1, Okay. So, if E equal to 1, C 2 equal to 1, sigma V equal to 1, sigma V prime equal to 1, then you can clearly see that E times C 2 or suppose I take C 2 times sigma V prime, okay, then that will be E 2 times sigma V is sigma V prime, and sigma V prime, the representation of sigma V prime is 1. So, clearly in this way, a very trivial way, the products of operations, they correspond to the product of representations. Okay. So, this clearly satisfies this condition. This is a one dimensional representation. So, this is a one dimensional okay. Now, you can have other one dimensional representations. So, for example, you could have the following: E equal to 1, C 2 equal to 1, sigma V equal to minus 1, sigma V prime equal to minus 1. Okay. Now, what you can see is that suppose I take E times C 2, I get C 2, E times sigma V, I get 1 times minus 1, which is minus 1, okay, and all that works. Now, suppose I take C 2 square, C 2 square is just 1 square, that is 1. Similarly, if I take sigma V square, that is 1, which is identity. So, sigma V times sigma V should be identity. So, sigma V square should be 1, and so on. But you can also see that suppose I take C 2, suppose I take sigma V times C 2, okay, sigma V times C 2 should be sigma V prime. So, if I take sigma C 2 equal to sigma V prime. Now, sigma V has a representation minus 1, C 2 has plus 1, okay, and this is equal to minus 1. So, you can clearly see that this is satisfied. Okay. So, you can have, so this is also another one dimensional representation. Okay. So, this is another one dimensional representation. Okay. You can construct many more such representations. I will not bother with all the details, but basically it shows that you can construct 2 dimensional, you can construct 3 dimensional representations, and so on. Okay. And there is really no restriction on what you can do. Okay. So, let us so this shows that we have seen that this 3 by 3 representation. Okay. So, 3 by 3 representation okay. So, the 3 by 3 or the 3 dimensional representation so you can always use this 3 dimensional representation. So, if I had used a 3 dimensional representation for this group, okay, if I had used a 3 dimensional representation for this group, okay, then what you can show is that it will actually factor. So, the set of 3 dimensional matrices can be factored into smaller matrices. Okay. So, we could have used a 3 dimensional representation, we could have used, and here we used 1 dimensional representations. Okay. And what we want to see is that is there any fundamental difference between various representations. Okay. So, is there any fundamental difference between, I will say, different types of representations. Okay, is there any fundamental difference between different types of representations? And the other question we want to ask is, I can always, since I have a one dimensional representation, I can always construct higher order representations very easily. If I can always make since I can construct a 3 by 3 representation, I can construct a 6 by 6, 9 by 9, 12 by 12. I can construct any representation, any dimensional representation I want. Okay. So suppose I have this one dimensional representation, then I can always construct a two dimensional representation. For example, I can say E is equal to 1 1 0 0, C 2 is equal to C 2 is I am using. So I can construct a two dimensional representation starting from this. So 1 1 0 0, sigma v 1 1 0 0, sigma v prime equal to 1 1 0 0. So you can see that again everything is nothing but the identity matrix, and products will also be identity matrix. This is a two dimensional representation. Okay. Similarly, if you want, I can construct three dimensional representations by just putting this, or I can put this and the other one. So just to make, so I put 0 1 0. So identity will always be this way. C2, for C2 again I will just take 1 1 1. For C2 prime I can take, or for sigma v I can take 1 0 0 0 1 0 0 0 minus 1, and sigma v prime I can take as the same. Okay. So I can always take this representation, and you can clearly see that that since 1 1 1 1 is a representation, and 1 1 1 1 is a representation, and 1 1 minus 1 is also a representation. So this will also be a representation, and I can keep doing this. I can keep doing this on, and I can make all kinds of representations. Now so this is a 3D representation. Okay. Alternatively, I can also use the usual 3D matrix representation of the usual 3 by 3 matrix representation. So there are many possible representations. Okay. Now we'll distinguish something called we'll distinguish between reducible and irreducible representations. Okay. And this can be seen. So let us take this representation. So 1 1 1 1. Okay. So this would be what is called an irreducible representation, whereas something like this would be what is called a reducible representation. The reason why this is called a reducible representation is the following, that if you factor these into blocks, okay, then each of these is also a representation. Okay. So each of the blocks is also a representation. Similarly, I can factor this into blocks. I can factor it either into blocks this way, so if I factor it this way, then I get a one dimensional representation. So we already saw that this is a one dimensional representation. Okay, 1 1 minus 1 minus 1, and then this is an example of a two dimensional representation. So this 2 by 2 matrix is an example of two dimensional representation, and everywhere else you have diagonals. Okay. So basically, if I take a product of any two elements, I can do a product of these matrix, and I can do a product of this, and I can put 0 everywhere. Okay. So these are examples of reducible representations. Okay, whereas this is an example of an irreducible representation, in the sense you cannot reduce it to smaller dimensional representations. Okay. So the way to do it formally is to see that, suppose you had a representation, suppose you had a general representation, okay, and if you could so you keep trying to factor it into block diagonal forms. into block diagonal form, okay, then you will get something that looks like this. A, you might get something like this, B, C, and you will get zeros everywhere else. Okay, so you get zeros for all the. So this is a general. This is one part of the matrix. This is another piece of a matrix. So all these are square matrices. So A, B, C are square matrices. Square matrices. So you keep doing this. You keep breaking into block diagonals till you cannot break it anymore. Okay. And then what you find is that each of these A, B, C's are also representations, and if you cannot factor it anymore, then they are called irreducible representations. Okay. So I will just give an example of a matrix. So here is an example of a we will start with a matrix. Okay. So so the important part is each operation should be factored into such block diagonals. So factor each operation. Okay. So if you can factor every operation in the group into such block diagonals, then that representation is called a reducible representation, because you can reduce it to smaller representation. Then each of these is also a valid representation. Okay. So let us take an example. Suppose I had a matrix. Suppose my various operations of the group. Okay. So my various operations of the group, they can be fact. So one example, let us say, so the identity operation will always be block diagonal. Okay, so the identity will always be diagonal. Okay. Now if I had other operations and they had this structure. So this is one operation, this is another operation. I will just take 1 minus 1 minus 1 1 0 0 0 0 and then I had, let us say, 1 0 0 1 I had 1 and okay, let me take minus half root 3 by 2 0 root 3 by 2 minus half 0 0 0 1. Okay, so suppose I had something like this. Okay. So if this is a representation of one operation, and if all the operations, so I see that I can immediately factor this into this form. So this immediately factors into something like this. Okay. So this has a, now if all the operations in the group can factor into the same form, for example, I could factor this also into the same form. I can do this for all the operations of the group. Okay. Then you say that the 6 dimensional representation is not an irreducible representation. So if such block diagonalization can be carried out for all matrices representing various operations of a group Okay. So if you can do such a block diagonalization for every for the matrix corresponding to each and every symmetry operation, okay, then we say that the representation is reducible. Okay, so we say that it is reducible, and each of these individual. So, you keep doing this until you cannot do it anymore, and each of these 2 by so this is an example of an irreducible representation, because you cannot make this into any smaller block. This is an example of an irreducible representation because it is one dimensional. One dimensional representation by default is irreducible. Similarly, this is an example of an irreducible representation because you cannot break it into smaller blocks for all the elements. Okay, actually in these two you can break it into this, but if there are other elements which mix the others, okay, then so you can also break this like this. Okay, so you can also go this way. Okay, but this 2 by 2 representation is an irreducible representation. Okay, so basically what we try to do is to break up our matrix into blocks such that there is zeros outside the blocks, it is 0. Okay, and you try to do this for all the elements. Okay, so irreducible representations cannot be factored into smaller representations, smaller dimensional representations. Okay. So, what we have concluded by all these arguments is that there are two kinds of representations. There are reducible and irreducible representations. The reducible representations are those representations which can be factored into smaller blocks. Okay. The irreducible representations are those that cannot be factored into smaller blocks. For example, this one is an irreducible representation, but it is very important to keep in mind that this factoring has to be possible for all the symmetry operations. It is not, if it happens for only 1 or 2 symmetry operations, it is not, you do not say that this is a valid factorization. So, when you are looking to see whether a representation is reducible or irreducible, you should try to do this block diagonalization for all the elements, for matrices corresponding to all the symmetry operations. Okay. Now, the irreducible representations are the ones that are more relevant. Okay. So, you can already see that irreducible representations are the important representations, because I can always, using irreducible representations, I can always make more and more representations. Okay. So, the relevant representations are the irreducible representations. They are like you cannot using those, you can always make up. See using such irreducible representations, I can always make up a bigger reducible representation. Okay. So, it is always of interest to know what are how many fundamentally different irreducible representations are there in any group. Okay. And this will be the topic of something called the great orthogonality theorem, okay, which tells you how many irreducible representations are there. Okay. So, last thing that I will mention is that each of these matrix representations, each of these. So, this is a matrix representation of identity, in a 2 dimensional representation. This is whatever operation in a 2 dimensional representation. Now, all of these will have the properties of representations, that is that the trace of 2 elements in the same class are the same. So, the character of any 2 elements in any representation will be identical if the 2 elements are in the same class. Okay. So, in the next class we will look at the great orthogonality theorem and what it tells you about the various representations that are possible. Okay.